Now, we continue with considerations that are in regard to rationalizing strengths of Bronsted-Lowry acids, which we do in terms of assessment of effective negative charge density on the conjugate base of the acids. Please recognize that these considerations are about parent acids which are molecular in nature, not hydrated metal ions, which you talked about yesterday. So far, in our grab bag of factors, stabilization of negative charge density by charge to size ratio, electronegativity, orbital electronegativity, induction, which is an extension of the idea of electronegativity. Keep in mind that induction depends upon proximity to site of development of negative charge, to atoms which can stabilize negative charge density by induction, atoms of substantial electronegativity. Resonance. And now, principle of maximum overlap, which in the main is a theoretical consideration, but it applies. You talked, I should imagine, in 2045 about bond formation from a theoretical standpoint as a consequence of overlap of orbitals. Atom A with a valence orbital interacts with atom B with a valence orbital, like an H atom with an H atom, simplest possible case. Forming a shared electron pair as these atoms get together to make the bond. Pictorial representation of such Lewis structure. Where do these electrons reside from a theoretical standpoint? Where does the bonding electron pair reside from a theoretical standpoint? In atomic orbitals, 1s specifically. Here, in an overlap region formed by overlap of the 1s atomic orbital of this H atom with the 1s orbital of this H atom. What might that look like? Well, we've got pictures over here. If the atoms are of the same size, then their valence orbitals are the same size. And we can draw a picture of the overlap interaction like this. Now, notice what we've written here. Orbital overlap is most effective, and bonding electron density is closer to nuclei of bound atoms when the covalent bond formation interaction is between small atoms of similar size rather than small atom with a large atom, or large atoms with each other, even though the large atoms may be of similar size. In this instance, we get a greater degree of overlap of the valence orbitals which overlap with each other to provide a parking place in space for the bonding electron pair. Now, I don't know if you mentioned or had this mentioned to you in 2045, but from an orbital overlap standpoint, if the area of the overlap region relative to the total orbital surface area is large, then we'll have strong overlap, strong bond formation. Now, when will this area of overlap region relative to total orbital surface area be greatest? When? we've got relatively small atoms with small valence orbitals interacting with each other. Did you see any pictures like this in 2045? I'm curious. I can't say that I know a whole lot about these theoretical considerations, but I think in essence we've hit at it. The upshot of this is to realize when relatively smaller atoms interact with each other to make covalent bonds, we well expect these covalent bonds to be stronger, as opposed to a small atom with a larger atom or two larger atoms interacting with each other. If nothing else, recognize that when the bond formation interaction is between smaller atoms, the bonding electron density will be closer to the mutual nuclei of the atoms which interacted with each other. And we're talking about atoms like carbon and nitrogen and oxygen, which we know to be the atoms in the periodic system, which most commonly exhibit multiple bond formation in their chemistry. Atoms of appreciable electronegativity compared, for example, to larger atoms or metal atoms. So, stronger bond here, weaker bonds here. As far as I'm concerned, that's enough for us at this stage of the game. Expect, from a principle of maximum overlap, orbital overlap standpoint, stronger bonds when the bond formation interaction are with smaller atoms and atoms of, on a relative basis, greater electronegativity compared to larger atoms. Now, we'll see a couple of considerations in regard to this for bond strength assessment that we will talk about in a few moments. A comment about solvation in Bronsted-Lowry acid strength. First, just for fun, recognize that the word is solvation, not salvation. I don't know how to provide to you the salvation part. As far as I'm concerned, that's up to you. But solvation is just a term which refers to the interaction that takes place between solvent molecules and the species which are produced when Bronsted acids behave as such in a solution of that solvent. Now, what do Bronsted acids do? They're all H+ givers. And how do we measure the strength of a Bronsted acid? Well, in water solvent, we measure the strength of a Bronsted acid by its ability to protonate water and form hydronium ion. If we were, however, to do Bronsted acid strength studies in methanol, the simplest alcohol, an organic molecule, with an organic molecule being classified as anything which has got at least one carbon-hydrogen bond in it. The OH group, which is part of the methanol molecule, is why this stuff is classified as an alcohol. You'll learn more about that in organic chemistry class. So, if we consider the strength of water in, of acetic acid in water solvent, then we are looking at the extent of this equilibrium reaction before equilibrium is established. And we look at the strength of this, the extent of this reaction in terms of Ka for acetic acid. But if we were going to study acetic acid and its ability to behave as a Bronsted acid in methanol, then we look at the establishment of this equilibrium reaction and measure Ka for acetic acid, but now in methanol. Now, from a solvation standpoint, in which of these solvents, water or methanol, do you expect these reactions to proceed left to right as written to the larger extent before equilibrium is established? Or, put another way, Ka acetic acid in water versus Ka acetic acid in methanol, which Ka value do you expect to be larger? Or do you expect them to be the same? Hint, pay attention to the fact that when Bronsted acids do their thing, what kind of particles do we always form? Ions. Always form ions. So the answer to this question lies in recognizing which solvent, in our case solvent water or solvent methanol, will stabilize ions more effectively. Well, from a Coulombic standpoint, from an electric standpoint, which molecule is more electric in character? Which molecule is more polar? Water. That's why Ka acetic acid greater in water than in methanol. Because hydration interactions, solvation by water molecules, are stronger than solvation by molecules like methanol because they're not nearly as polar. Enough said. That's not all that important to us now. I wrote a note accordingly because we have focused on Bronsted-Lowry acid-based chemistry, practically speaking, strictly in water solvent. You'll likely be expected to consider solvation effects for properties of materials like Bronsted acidity in organic chemistry class. More so than what we've done here. Now, some more examples to see what we select from our bag of factors that we've assembled. I've written them all up there. Bronsted-Lowry acidity of oxoacids. Well, first of all, what's an oxoacid? An oxoacid is a species which has got in its structure and composition one or more peripheral oxygen atoms. So, if you see the formula for an acid or a potential acid, because it's got hydrogen in its composition, and the formula also contains oxygen, how are you going to find out if this stuff can be classified as an oxoacid? Like the water molecule. Got oxygen and hydrogen. Hypochlorous acid, HOCl, HOClO, HOClO2, HOClO3. Here's a whole series of oxygen-containing acids. Except for, I thought I had HCl here. No. There's a whole series of oxygen-containing acids. Which of these molecules would be classified as an oxoacid? Well, water molecule. Is this a peripheral oxygen atom? No. So a water molecule is not an oxoacid. How about hypochlorous acid? Now let me remind you about another problem that will arise regarding formulas as they are written commonly by textbooks. Textbooks generally write the formula for this acid this way. Now, from a relative electronegativity standpoint, that's understandable. Because usually in writing formulas, you start with the chemical symbols for the atoms of lower electronegativity and migrate toward the symbol for atoms of higher electronegativity. So in that regard, this formula is okay. But as we have noticed, the most important property of any species is its structure. And this formula belies the structure of hypochlorous acid. because hypochlorous acid, have I got it up there? No. Has this structure. The hydrogen atom is oxygen bound, not chlorine bound, which is implied by this textbook formula. So would you classify hypochlorous acid as an oxoacid? No. Hasn't got a peripheral oxygen atom. But when you get to this, which is chlorous acid, or hydrogen chloride, this which is chloric acid, or hydrogen chlorate, and this which is perchloric acid, or hydrogen perchlorate, which you may recall is in our acid-base table appearing as the strongest acid in the acid column in our acid-base table, back to chapter 18. These are all oxoacids. Now, what is the consequence of a molecule which has got peripheral oxygen atoms in regard to stabilizing negative charge density? We really have talked about this already, haven't we? It's induction. And you should realize that oxygen atoms will stabilize negative charge density by induction more effectively than any other atom except fluorine. The only atom that's more electronegative than oxygen. So, to go further with this consideration, I've written the Lewis pictures so as to show the shape of these anionic species. The Lewis pictures for the conjugate bases of these two oxoacids. And in a moment we'll talk about conjugate base for this oxoacid. It should be immediately obvious to you that this base is going to be a weaker, more stable, less reactive base than this base. Because here you have 3 oxygens to stabilize negative charge density, as well as the central chlorine atom, which is of appreciable electronegativity, relative to 2 peripheral oxygens and the central chlorine atom. So, simply put, since the conjugate bases of each of these species bears a charge of -1, the conjugate base with the greater number of oxygens to more effectively stabilize negative charge density by induction will be the more stable base. Upshot, this is a good deal stronger acid than this. This you know to be a very strong acid. In fact, this is the strongest acid appearing in our acid-base table. Now, I asked you a couple of classes back a question which is related to this. Let's take a look at that question now. Remember this question? I asked you to consider the relative Bronsted-Lowry acid strengths of these 3 acids. Nitrous acid, nitric acid, and this is the hydrogen carbonate ion. Now you already know what the relative strengths are of these 2 acids. This is categorically one of our strong acids, and this is quite a weak acid. Based on what we've said, how do you expect the acid strength of this nitric acid to compare to this nitrous acid? This one's stronger. In fact, it's a good deal stronger. This has got a Ka value on the order of 10 to minus 4, 10 to minus 5. Now, I asked you, in regard to these three acids, to also think about the effectiveness of negative charge stabilization by resonance. Notice, if you will, that each central atom, nitrogen in the nitrite ion, nitrogen in the nitrate ion, and carbon in the carbonate ion, are all hybridized how? They're all sp2 atoms. So, bond angle G whiz 120 degrees for each of these. For these two species, the bond angles are perfectly 120 degrees. Would you expect a nitrite ion to show a bond angle that's perfectly 120 degrees, or perhaps somewhat smaller or somewhat larger than 120 degrees? Somewhat smaller, somewhat larger. Well, it's a tough call because you've got multiple bonding electron density at the bond sites repelling each other, and a non-bonding pair on the central atom. Now, the central atom will repair a single bonding electron pair more effectively than single bonding electron pairs repel each other. But when you build up the electron density at a bond site beyond a single bond, then you increase repulsion between the bonding electron densities that you find at the bond sites. So, about the only way to resolve the issue for sure is to take this thing to the laboratory and measure the bond angle. If my memory's right, this is about 119 degrees. A little bit smaller. So the non-bonding bonding pair repulsion exceeds somewhat the bonding pair repulsions. In any case, back to resonance stabilization of negative charge density. You know how to write the other resonance forms for these species. I've placed the formal charges on the appropriate component atoms of these species. Of course, the true formal charge on a peripheral oxygen atom for nitrite ion is how much? The true formal charge. Is it -1 and 0? The true formal charge, what is it? Minus a half. Because these oxygen atoms are electronically equivalent. The trouble is, I cannot draw a picture which will be in any fashion a reasonably accurate representation of a partial multiple bond. From a bond order standpoint, the NO bonds are 1.5 for the nitrite ion. How do I draw a picture of a half a bond? I can't do that. Nitrate ion. NO bond order, 4/3. What's the true formal charge on a peripheral oxygen atom for nitrate ion? What is it? The true formal charge for an oxygen atom, nitrate ion, -2/3. Don't forget the sign. -2/3. Because again, these oxygen atoms are electronically equivalent. Now, based on resonance, We can argue that this is certainly a weaker, more stable base than this because you've got an additional oxo-oxygen to stabilize negative charge density by induction. That's correct. That fits the facts. But what about resonance stabilization? By resonance, which of these anions does a better job of stabilizing negative charge density? By resonance. Is it nitrate ion or nitrite ion? The simplest way to answer this question is to ask yourself, how many resonance forms can I draw? Well, how many resonance forms for this? 2. More resonance forms, more negative charge density smear. Better stabilization here because you have a greater degree of resonance. By resonance, you're spreading this negative charge over 4 atoms. Here only 3. Now what about carbonate ion? How do you think resonance stabilization of negative charge density by carbonate ion compares to that for nitrate ion? Three resonance forms again? Actual formal charge on a peripheral oxygen atom, on an oxygen atom for carbonate ion, actual formal charge? Negative 2/3, just like this. Of course, the difference lies in the fact that this central atom's got a plus formal charge. Carbon central atom, carbonate ion, 0 formal charge. All right? If then we realize that from a structure standpoint, these anions are identical. They're both trigonal planar, perfectly so, with sp2 hybridized central atoms. And I have just as many resonance forms for carbonate ion as I do for nitrate ion. And I have identical formal charges for the peripheral oxygen atoms for each. Why is this so much a stronger acid than this? Same amount of oxo-oxygens, same number of resonance forms, same actual formal charge for oxygen atoms. Why is this so much a stronger acid than this? Don't miss the obvious. It's what? It what? Well, nitrogen is more electronegative than carbon. 3.0 versus 2.5. Do you think that would be enough to account for the huge difference in the acid strengths of these things? How about the negative charge itself? That's what counts the most. This damn thing is -2. This is only -1. Now, let's look at these two. To assist us in getting at HOBRO3 and its acid strength versus HOClO3, keeping in mind again that HOClO3 is perchloric acid. I don't write it, the formula, in textbook fashion as HClO4 because that belies the structure. Notice the number of similarities between the conjugate bases of these acids. Of course, if you want the lowest structures for the conjugate base of perchloric acid, just take what I have here and erase bromine, write in chlorine. How are the central atoms hybridized? sp3, sp3, no difference. Bunch of oxo-oxygens to stabilize negative charge density. Surely That's one of the primary factors why perchloric acid is such a strong acid. How do you think the strength of this compares to this? You think this would be about as strong, perhaps stronger?
Should one of them be a chloride? But both of your diagrams have the
Yeah. Oh, no, I'm saying if you want the Lewis structures for the anion of this, just take these pictures, erase bromine, put in chlorine. Okay? We're going to go forward with this consideration in a moment. I'm just asking right now how you think the acid strengths of these two molecules might compare. Stronger acid? How many vote for this one? How many vote for this one? Well, let's go and look in greater detail at the factors. Bromine electronegativity, 2.8. Chlorine electronegativity, 3.0 or 3.1 on some scales. Not much difference in their electronegativities. Size. Which is the larger anion? Perbromate or perchlorate? Perbromate, because bromine is a good deal larger atom than chlorine. You think there's really a whole lot of difference in size between perbromate and perchlorate? You think there's a whole lot of difference in size? Do you recall that when we started this analysis, we looked at the relative acidities of these two molecules and found out that this is the stronger acid? Argument: the bromide ion is a good deal larger than the chloride ion. So even though chlorides derive from chlorine, which is more electronegative than bromine, this more effectively dilutes negative charge density as a function of charge to size ratio. And what's the predominant factor? Well, if we argue negative charge density stabilization by electronegativity, we'd argue this to be the weaker base. But that doesn't fit the facts. This is the weaker base. So, from our bag of tricks, from our collection of factors, we're going to argue charge to size ratio is more important in deciding between charge densities, effective charge densities of these anions compared to each other, which is why this is the stronger acid. All right? Back to these. Since bromine is bigger than chlorine, the perbromate ion is larger than the perchlorate ion. Now, what about this Lewis picture? Is this a legitimate Lewis picture for this species? For BrO4 minus, is this a legitimate Lewis picture? What we did was to examine this Lewis picture, and on examining it, assess formal charge. -1 for all the singly bonded oxygen atoms and +3 for the central bromine atom. That's a considerable degree of formal charge. Is it possible to rewrite this Lewis picture and minimize formal charge? Well, that's what I did. I said, let's imagine a bromine-oxygen double bond here and here and here. Not a fourth bromine-oxygen double bond, because that would migrate the negative charge to the central bromine atom. We don't want to do that because oxygen is more electronegative than bromine. So we always want to stop with a Lewis picture after we've minimized formal charge as much as possible. We still want to stop with a Lewis picture that's got the formal charge, the negative formal charge, on an atom of greater electronegativity, oxygen being more electronegative than bromine. So by converting this Lewis picture to this Lewis picture, we've reduced formal charge a lot. Do you accept this Lewis picture? Is there anything wrong with bromine, an atomic member of period number 4? Is there anything wrong with bromine having 1, 2, 3, 4, 5, 6, 7 electron pairs in its valence environment? Nothing wrong with that. Would there be anything wrong if I consider reduction of formal charge for chlorate per chlorate ion?
Yes.
Anything wrong with this? Chlorine's an atomic member of period 3. How many valence electrons can you put in the valence environment of a period 3 atom? We played this game before. Now let's put it to use. How many valence electrons can you put in the valence environment of a period 3 atom?
18.
18! Oh, so this is okay for chlorate. So if induction and resonance stabilize negative charge density as effectively for BrO4 minus as they do for ClO4 minus, with the difference being 0.2 electronegativity units in favor of chlorine, if we found over here that charge to size ratio means more than electronegativity, could we translate that to this issue? And say, since bromine's bigger than chlorine, we know the perbromate ion is bigger than the perchlorate ion, so on that basis we could argue this to be a weaker, more stable base than perchlorate ion. That's fair. But the truth of the matter is, these acids are each very strong, but this one is a little stronger. This one is a little stronger. So now let's fine-tune this analysis. When it comes to induction and inductive stabilization of negative charge density, did we not find out that proximity, the nearness of the site of negative charge to the atoms which stabilize by induction matters? Are the oxygen atoms a little bit farther apart from each other for this, the larger anion, than they are for perchlorate ion? So, if that matters, we can get an idea why perchlorate ion is a somewhat more stable base. But what about resonance? Because if we're going to accept this Lewis picture, because it doesn't violate any of the rules of the road for making Lewis pictures, if we accept this Lewis picture, then we're recognizing that resonance is important for this species. So we're getting resonance stabilization of negative charge density as well. We got induction, we got charge to size ratio, we've got resonance. Which do you think of these anions? Perbromate put the chlorine back, perchlorate, would stabilize negative charge density more effectively by resonance? Or do you think they would stabilize by resonance with equal effectiveness? What do you think?
Equal.
Equal? What do we say over there? The practical application of this PMO stuff.
Smaller and it's better.
Shall we expect stronger covalent bonds between chlorine and oxygen or bromine and oxygen? Chlorine and oxygen, because they're similar, more similar in size. Bromine, oxygen, 2 periods removed from each other. Chlorine, oxygen, only 1. So from a PMO standpoint, we can also argue why this is a more stable and therefore weaker and less reactive base than perbromate. A lot of things to think about. But again, regardless of all these arguments which we've assembled, there's only one way to know the answer to any of these questions. on an absolute basis, and that's go to the lab and make measurements. Now, let's fine-tune the size comparison. We've recognized over here, because the facts dictate such, charge to size ratio means the most. If we try to rationalize the difference in the acid strengths between HCl and HBr, based on electronegativity, we're going to argue HCl is the stronger acid. And we'd be wrong. So we opt for the charge to size argument. Big difference in size between these two. Is there also a big difference in size between these two? What do you think?
Yes.
I got to vote for yes.
No.
Oh, I got to vote for no. This is fun. We got opposing votes. We have to send it to Congress. Okay? Now, size difference. Let's imagine that a bromine atom is, well, what shall we make it? A quarter. Chlorine atom is a nickel. Oxygen atoms are dimes. Okay? Bromine atom's a quarter. Chlorine atom's a nickel. Oxygen atoms are dimes. Now, I'm playing this game on the basis of believing you know the relative sizes of a quarter and a nickel and a dime. Is that fair? Of these three pieces of U.S. coinage, you know the quarter is bigger? And the dime is the smallest. Good, we know that. Wonderful. Now, from a monetary comparison, 25 cents, 5 cents. 5 times worth 5 times more, right? Like its size being much larger. Now it's worth 5 times more. Okay? Now look what we did to convert the bromide ion to perbromate and chloride ion to perchlorate. As things stand, this is 5 times this, right? 25 cents nickel. Now I'm going to put on 1, 2, 3, 4 dimes. What's this worth now? Not hard, 45 cents. And this is now worth 65 cents. Originally, this thing was worth 5 times this thing. How do they compare now? They're pretty close to each other now, aren't they? Compared to 5 to 1. Okay? The point of this is to realize is when you start stacking all these identically sized oxygen atoms on the periphery to build the perbromate ion from bromide ion and the perchlorate ion from chloride ion, what do you do to the size differential? You make it far less significant. It's this: if I had 2 giant boxes, and in one box I put a basketball, and in the other box I put a soccer ball. You know the basketball's a lot bigger than a soccer ball. Okay? But what happens to this difference in size if to the box containing the soccer ball I add 50 more soccer balls, and to the box containing the basketball I add 50 soccer balls? Will the total volume of this basketball plus the 50 soccer balls be much different than the total volume of the soccer ball plus the 50 soccer balls? Hardly any difference at all. But if I compare the volume of a basketball to a soccer ball, I got a volume that I'll bet's more than twice as large. It's like this. So we can get a better idea why this charge to size issue is much more important here than it is here, because there really isn't that much difference in size between perchlorate and perbromate. All right? Now what about HCl versus this or this? This is chloric acid and perchloric acid. Now if we go back to our acid-base table, we know that this ion is a more stable, less reactive base than this ion. This again is ClO4 minus. Now we're throwing ClO3 minus into the mix. We know this acid is stronger than this acid, but these two acids are both very strong acids. We're just taking data from our acid-base table, if nothing else. How do you think this one fits in compared to this? We know this one is a weaker acid than this. Induction favors the stabilization of the conjugate base of this more so relative to this because of the additional peripheral oxygen. How about these versus each other? Any idea? If you look up the data, you'll find out that Ka for this is a lot bigger than Ka for this. Interesting, isn't it? Now, what's the difference? Well, for HCl, we got this minus charge smeared on the chloride ion when this thing does its acid thing. For chlorate ion, if we go to the picture without multiple bonds, we'd have this formal charge distribution. And then we could go back and say, well, can I reduce this formal charge distribution? Sure. Let's imagine these chlorine-oxygen bond sites have multiple bond character and play this game just like we did for perbromate ion and perchlorate ion. And reduce the formal charge on this oxygen to 0. We do that, we change the formal charge on central chlorine to +1. Another double bond. Now we've reduced the formal charge on this oxygen to 0, and now the formal charge on chlorine has been reduced to 0. And we're not going to imagine any more double bonding, multiple bonding, because that would transfer the minus formal charge to the central chlorine atom. We don't want to do that because this atom is more electronegative. So we'll leave this here. So now by this presumed resonance, we've again stabilized formal charge. We've reduced the distribution of formal charge, reduced formal charge itself, pardon me, much more effectively than what we started with. And here we got 1, 2, 3, 4 atoms of substantial electronegativity to stabilize negative charge density by induction. And we know the induction means a lot because the anion of this is a weaker base than the anion of this. But notice, for any of these oxo acids, the minus charge always winds up on oxygen. For HCl, the minus charge can't be any place but on chloride ion. So if it's true, and it is true, that chloride, HCl, is a much stronger acid than this, then we're finding out that we are stabilizing negative charge density more effectively by smearing it on this large chloride ion, all by itself, compared to, imagine smearing over 1, 2, 3, and possibly 4 atoms, and stabilizing by mutual induction of these 4 atoms. Interesting, isn't it? If nothing else, this gives you an idea why, when textbooks write a formula like this, that's horrible. Because if you're going to interpret this formula literally, you'd believe that the bond structure of this molecule is this. And now when H went away, you'd have this minus charge on chlorine. So if you got a minus charge on chlorine, which is stabilized by induction by oxygen, you'd have to have a base that's weaker and more stable than this thing. Another thing that's grossly wrong about formulas like this. Because when we realize the facts, let's do it this way. That the minus formal charge for this ion is really principally on oxygen, we can recognize why this is a much stronger base than this. Because independent of electronegativity, how do chlorine and oxygen compare size-wise? This is a lot smaller. And when you concentrate that charge on a much smaller atom, you make this a much stronger base. And why do we believe this argument? Because this is a much stronger base. We go and look up the data and find out that that hypochlorous acid, this thing, Ka, much, much, much smaller than that for HCl. I went into this just, if nothing else, to show you how important this structure consideration is. Well, let's have a little bit more fun and go to this. To help us with this, I've already taken the liberty of putting the Lewis pictures on the board for the conjugate bases of these two acids. Now let's see what we have. If we minimize formal charge for chlorate ion, then we have this picture, which we just looked at. And here again is the Lewis picture for nitrate ion. We have chlorine and nitrogen central atoms, which are of approximately equal electronegativity, but chlorine a little bit higher, at least that's what the data suggest. 1, 2, 3 peripheral oxygen atoms to stabilize negative charge density by induction, just like this. And if I'm going to accept this Lewis picture, then I am arguing resonance is an important property for chlorate ion, which we already know is an important property for nitrate ion. So I've got here a species which is a little bit larger than this. I've got here a species which has got as many oxo-oxygens as this to stabilize negative charge density. I've got two anions which are each -1 total charge. And I've got a species here which is stabilizing negative charge density by resonance, if we're going to accept this Lewis picture. So how do I expect these bases to compare strength-wise? How do I expect the parent acids, nitric acid for this, to compare strength-wise? Well, if I go back to what we just talked about, and recognize that this is a good deal stronger acid than this, I should not be surprised to find out that nitric acid is a good deal stronger than chloric acid, given that we know nitric acid is also categorically one of our strong acids in our acid-base table, has got a large Ka value. Not as big as HCl, but still a pretty large Ka value. Well, what's going on here? Why is this base so much more stable and less reactive than this base? I mean, stable from a negative charge density standpoint. Why is that? PMO is an argument, for sure. Because these are neighboring atoms from period number 2. These are from different periods. So I expect stronger covalent bonding here. But there's one remaining important property of these two species which we have not yet discussed, even though it's implied by what I have on the board. We know this is an sp3 central atom. This is an sp2 central atom. Do you think that has any bearing on negative charge density stabilization? In particular by resonance? Well, tell me. Have you seen these pictures before? Pardon me, these models? You've seen these models before, haven't you? What are these models of? Three-dimensional figure eights?
Those are p orbitals?
Tops of bowling pins glued to each other? P orbitals? When p orbitals overlap with each other to make a pi bond, what does this overlap look like? This a pi bond? Oh, that's a sigma bond.
It's like them.
You remember that a principal difference, if not the main difference between sigma and pi overlap, is the number of overlap regions? When you make a sigma bond, you got one overlap region between the orbitals which interact with each other. Whereas when you make a pi bond, you got two overlap regions. Can d orbitals make pi bonds? Did you see anything about d orbitals in 2045? Here's a couple of d orbitals. That look like a pi bond? Can d orbitals make pi bonds with d orbitals? Right. D orbitals can make pi bonds with d orbitals. Now, two p orbitals overlap with each other in pi fashion. Which pi bond is stronger? This one. We talked about Y earlier with PMO. Now, what's the shape of this thing? It's a derivative of tetrahedral. But you got to have 4 peripheral atoms to have a tetrahedron. What's the shape of this thing? What is this thing I'm holding? Can you see it? Trigonal pyramid. So, Another main difference between these two anion species is that this is trigonal pyramidal, whereas this is perfectly trigonal planar. So I made a model of our nitrate ion, recognizing that nitrogen and oxygen atoms each have valence 2s and 2p orbitals. But if I'm going to make pi bonds, can I do such with s orbitals? No. S orbitals can only get involved in sigma bond formation. So for pi bonding in the nitrate ion, I've got to recognize p orbital overlap with the nitrogen central atom to each of the 3 peripheral oxygen atoms. And of course, these fancy loops simulate the p orbitals. Notice that for this trigonal planar nitrate ion, these p orbital loops are all mutually parallel. These are not perfectly parallel. Is this p orbital, is this pi bond as good as this pi bond? Much more effective overlap here. So notice for this trigonal, weak lobe. For this nitrate ion, because of a trigonal planar geometry, all the p orbitals are mutually parallel, which gives us the most effective possible overlap between and among these p orbitals to give us a stable pi system. Now then, back to chlorate ion with an sp3 hybridized central atom. Model. I don't care how you choose to orient the lobes of the p orbitals on the peripheral oxygen atoms. For something like chlorate ion, can you get as effective orbital overlap for this thing as you can for the planar stuff? No, because this thing isn't planar. So what we've now realized is that for resonance, multiple pi bonding involving 3 or more atoms, for resonance to be an important property of a species, what kind of hybridization are you looking for?
SP3.
SP2, because that corresponds to planar geometry. And the remaining part then is planarity. SP2 hybridization and planarity. It's important. The upshot of all of this is to realize that the trigonal planar nitrate ion has a much more stable pi system than the trigonal pyramidal chlorate ion, which is ultimately the argument, as I see it, that tells us why the nitrate ion is so much more a stable, less reactive base than chlorate ion, which of course tells us why nitric acid is such a stronger acid than chloric acid. Now, one more question since we're on this, because there is arguably a degree of resonance exhibited by species like chlorate ion or perchlorate ion, but it's not nearly as effective as it is for species like nitrate ion with its sp2 hybridized central atom and trigonal planar geometry. Look at this picture, or better yet, look at this picture. We've recognized that this central atom is sp3 hybridized, as it is for chlorate ion, for bromate ion. If we're going to imagine multiple bonding at these central atom, peripheral oxygen atom bond sites, what valence orbitals is the central atom using for this multiple bonding? For pi bond formation. Pi overlap. What valence orbitals is our central atom? Chlorine here, bromine here. Again, chlorine here. What valence orbitals? These atoms are sp3 hybridized. Can these central atoms be using any p orbitals for pi bonding? If it's sp3 hybridized, that means all of the valence p orbitals are part and parcel of the sp3 hybrid. Did you recognize in 2045 when you talked about hybrid orbitals and hybridization considerations that this idea of hybridization applies exclusively to the sigma system? Electron density in hybridized orbitals will strictly be sigma electron density. So, what orbitals can these central atoms use for pi bonding? What kind of orbitals are these? D. Chlorine, bromine, they got valence d orbitals? Yeah. So, one more bit of language. When we looked at this picture and imagined the advancement of non-bonding electron density from the peripheral oxygen atoms to the central atom to make partial multiple bonding at these bond sites, this has got to be p electron density, because you can't make pi bonds with s electrons and s orbitals. And the bromine central atom has got these kinds of orbitals available for pi bonding, d orbitals. So this kind of bond formation interaction is often described in this fashion. P pi to d pi. P representing the electron density that came from the oxygen atoms, to d pi, because the central atom supplied empty d orbitals to accept this electron density. Have we talked about a category of reactions, specifically at the end of chapter 19, which relates to this? Electron density came from the peripheral oxygen atoms to occupy empty valence d orbitals on the central atom. What kind of reactions did we talk about at the end of chapter 19 which relates directly to this? Remember this? Lewis base? Lewis acid? Did you learn anything yesterday about Lewis base, Lewis acid reactions in discussion class? Did you learn that when coordinate covalent bonds form, they're always categorized as a Lewis acid, Lewis base interaction, which is very much the essence of coordination chemistry, So I chose to mention that because that's what you started to talk about yesterday, and that's what we shall talk about in detail for our remaining gatherings.